The principle of least action determines the motion completely. Solving the equations, it gives us both the shape of the path and the position along it as a function of time. But if the problem is the more restricted one of finding only the path, with no reference to time, a simplified form of the principle can be used. Assume first that the Lagrangian, and so the Hamiltonian, does not contain the time, so the energy is conserved. Letting the final time vary with the coordinates held fixed, the last lesson gave the variation of the action as minus the Hamiltonian times the variation of the time. Now compare only those motions that satisfy conservation of energy. For such paths, the Hamiltonian is the constant e, and the relation becomes the variation of the action plus e times the variation of the time equals 0. Write the action as the abbreviated action minus e times the time. Substituting, the two terms cancel and one statement is left. The variation of the abbreviated action vanishes. The abbreviated action is the integral of momentum along the path. So among all paths that conserve the energy and pass through the final point, whenever they arrive, the true one makes that integral least. To use this, we must express the momenta through the coordinates and their differentials. We do it with the definition of momentum, using conservation of energy to eliminate the differential of the time. For the usual Lagrangian, kinetic minus potential energy, the result is that the abbreviated action is the integral of the square root of twice the energy minus the potential times the quadratic form of the kinetic energy. For a single particle, the kinetic energy is 1/2 mv squared, and the principle becomes the integral of the square root of twice the mass times the energy minus the potential taken along the element of path length. This form is due to Jacobi. In free motion, the potential vanishes and the integral is just the path length, so the particle takes the shortest route between 2 points, a straight line. With a potential, the square root of the energy minus the potential acts as a refractive index and the path bends.